Everything you see around you right now might be fake. Not metaphorically fake, not philosophically questionable. Actually, genuinely, literally fake. A computation, a rendering. Code running on hardware in some reality you've never accessed and cannot imagine. Your memories might be fabricated. The people you love might be non-player characters in an elaborate game. The laws of physics might be arbitrary rules chosen by programmers. The entire history of the universe, all 13.8 billion years of cosmic evolution, might be a simulation that started 5 minutes ago with all evidence of the past already embedded in its initial state. This isn't conspiracy theory or fringe pseudoscience. Serious scientists and philosophers are genuinely investigating whether we live in a simulation. Some estimate the probability at over 50%. A few think it's almost certain. They have arguments, testable predictions, and reasons that are harder to dismiss than you might expect. If you're ready to question the fundamental reality of everything you've ever known, subscribe and prepare yourself. What you're about to learn will either change how you think about existence or reveal the limits of taking philosophical speculation too seriously. We begin. The simulation hypothesis isn't new. Philosophers have questioned reality for millennia. Descartes wondered if an evil demon was deceiving him about the external world. Hindu and Buddhist traditions describe reality as illusion or Maya. The brain in a vat thought experiment asks how you'd know if you were just a brain being fed false sensory inputs. But modern simulation arguments are different. They're not asking whether you can prove reality exists. They're calculating probabilities based on technological trends and making specific claims about what a simulated universe would look like. The most influential version comes from philosopher Nick Bostrom. His simulation argument is actually quite simple and doesn't require assuming we're in a simulation. It just requires accepting one of three possibilities, at least one of which must be true. First possibility: civilizations destroy themselves before developing the technology to run realistic simulations of conscious beings. This could happen through nuclear war, environmental collapse, engineered pandemics, or any number of catastrophes. If advanced technology is inherently unstable and civilizations inevitably collapse before reaching simulation capability, then no simulations exist and we're definitely in base reality. Second possibility: advanced civilizations could run simulations but choose not to. Perhaps there are ethical prohibitions against creating conscious beings in simulated realities. Perhaps the technology is possible but just doesn't interest anyone. Perhaps civilizations transcend their interest in their own history and never bother simulating their past. Third possibility: advanced civilizations do run simulations, probably many of them. If creating simulated realities is possible and interesting, advanced civilizations might run billions or trillions of simulations. Each simulation might contain billions of conscious beings living lives indistinguishable from base reality. Here's where probability enters. If the third possibility is true, then simulated realities vastly outnumber base reality. There's one base reality, but potentially trillions of simulations. If you're a conscious being and you know nothing else about which reality you inhabit, probability suggests you're much more likely to be in a simulation than in base reality. The math is straightforward. If simulations exist and are numerous, most conscious observers are simulated. You're a conscious observer, therefore you're probably simulated. This is Bostrom's core argument. It doesn't prove we're in a simulation. It says that either civilizations can't or don't run simulations, or we're probably in one. At least one of these three options must be true. The argument assumes certain things about consciousness and simulation. It assumes simulated beings can be conscious, that artificial intelligence can experience subjective states indistinguishable from biological consciousness. If consciousness requires something non-computational, something that can't be simulated, the argument fails. But most scientists think consciousness is computational, that minds are what brains do, and brains are just very sophisticated information processors. If that's correct, then sufficiently advanced simulations could create genuine consciousness. The argument also assumes technological progress continues to the point where running realistic simulations becomes feasible. Current computers can't simulate an entire universe at quantum resolution, but computing power grows exponentially. Extrapolating forward, civilizations millions of years more advanced might have computational resources that dwarf current capabilities by factors we can't comprehend. They wouldn't need to simulate the entire universe at full resolution. They'd only need to simulate what observers experience. Most of the universe is unobserved. A clever simulation could render only what's being looked at, like video games render only what's on screen. The rest could be lower resolution or purely abstract, until observation requires detailed rendering. This makes simulation more computationally feasible. You don't need to simulate every atom in the observable universe. You just need to simulate sensory experiences of conscious beings and make sure the physics they test holds up under scrutiny. Some researchers think we might already be close to simulation capability. Not full universe simulation, but simulations convincing enough that beings inside them couldn't tell they weren't in base reality. Virtual reality is advancing rapidly. Brain-computer interfaces are improving. Within centuries, if not decades, we might create simulations containing conscious beings. And if we create one such simulation, we'll probably create many. Research purposes, entertainment, historical reconstruction, philosophical investigation. There are countless reasons to run simulations. Each simulation might itself create simulations, leading to nested layers of simulated realities. This creates a vast simulation tree. Base reality at the root, first-level simulations branching from it, second-level simulations branching from those, and so on potentially for many levels. The vast majority of conscious observers in this tree are in simulations, not base reality. The argument has received serious attention from scientists and philosophers. Papers analyze its logic, debate its assumptions, propose ways to test it. This isn't fringe speculation. It's mainstream enough that respected academics engage with it seriously. Critics point out flaws. The argument requires many assumptions about consciousness, computation, and the motivations of advanced civilizations. Maybe consciousness can't be simulated. Maybe simulating consciousness is possible, but illegal or universally considered unethical. Maybe civilizations invariably transcend their interest in such things. The probability calculation also gets murky. How do you count observers across different simulations? If one simulation contains 1 trillion conscious beings and another contains just one, should they count equally? The answer affects whether most observers are simulated. There are also logical issues about creating certainty from uncertainty. The argument says, if simulations are numerous, you're probably in one. But this doesn't create certainty. Even if 1 trillion simulations exist, base reality still exists too. Probability suggests you're simulated, but you might be one of the base reality observers. Despite critiques, the simulation hypothesis won't go away. It keeps attracting attention because it's genuinely difficult to dismiss. The logic isn't airtight, but it's not obviously wrong either. And unlike most philosophical speculation, it might actually be testable. Scientists have proposed ways to detect simulation. Limits on simulation resolution might create observable artifacts. The physics of our universe might contain hints that it's computed rather than fundamental. We'll explore these ideas later. For now, understand the core claim. Either civilizations can't or don't run simulations, or you're probably in one. This trilemma is what makes the simulation hypothesis compelling, despite sounding absurd. Your intuition says, this is ridiculous, that obviously you're not in a simulation, that reality is real. But intuitions aren't arguments. The simulation hypothesis doesn't care what feels true. It makes probabilistic claims based on reasonable assumptions about technology and consciousness. And those claims, if you take them seriously, suggest that everything around you might be rendered graphics in a cosmic video game, that your entire existence might be code running on some inconceivable computer in a reality you'll never access. That's the simulation hypothesis. The question is whether it's profound philosophy or clever nonsense. We'll spend the next sections trying to figure out which. If we're living in a simulation, there should be evidence. Simulations aren't perfect. They have constraints, shortcuts, bugs. If reality is computed, it might show signs of computation, anomalies that reveal the underlying code. Scientists have proposed several observable signatures that might indicate we're simulated. Some are subtle, requiring advanced physics to detect. Others are surprisingly straightforward, patterns in nature that could reflect computational shortcuts. Start with the most famous, the resolution limit. Every simulation has finite resolution determined by its computational resources. Simulate at too fine a detail and you run out of processing power. Programmers solve this by imposing minimum scales below which physics changes behavior. Our universe appears to have such limits. Quantum mechanics introduces fundamental uncertainty at small scales. You can't simultaneously know a particle's position and momentum with perfect precision. Energy and time have similar uncertainty relations. Space itself might be discrete at the Planck scale, the smallest meaningful distance. These quantum limits look suspiciously like resolution limits in a simulation. If you were programming a universe, you'd impose minimum scales to conserve computational resources. Why waste processing power simulating details below what anyone can observe? Critics respond that quantum mechanics has other explanations. Uncertainty principles emerge from the wave nature of matter, not necessarily from computation. The Planck scale might be fundamental for reasons unrelated to simulation, but the similarity is striking. Video games use level of detail scaling, rendering distant objects at lower resolution. Our universe seems to do something similar. Distant galaxies appear as points of light, not fully resolved objects. Only nearby objects render in detail. Of course, this has a conventional explanation. Light from distant objects is dim and spreads out, but it's also exactly what you'd expect if the universe renders only what's observed in detail and keeps everything else abstract. Quantum mechanics itself might be a computational shortcut. In the famous double-slit experiment, particles behave like waves until observed, then collapse into definite positions. Why does observation matter? One interpretation: the simulation doesn't bother calculating exact particle positions until something needs to know them. Particles exist as probability waves, computationally cheaper than tracking definite trajectories. Only when observation forces the issue does the simulation commit to a specific outcome. This is the quantum measurement problem, and it's genuinely puzzling. Why does the act of measurement affect what's being measured? Simulation theory offers an answer. Because calculating definite states is expensive, so the simulation waits until absolutely necessary. Conventional quantum mechanics offers other interpretations. Maybe particles really are in superposition until measurement. Maybe the wave function is real, not a computational shortcut, but the simulation interpretation is at least consistent with observations. Another potential signature: mathematical structure. Our universe is shockingly mathematical. Physical laws can be written as elegant equations. Symmetries and conservation laws emerge from deep mathematical principles. This could be how reality fundamentally works, or it could be how programmers efficiently code a universe. Mathematics is how computers represent everything. If our universe is computed, it should be deeply mathematical, and it is. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. Why does math work so well for describing reality? Simulation theory offers an answer. Because reality is mathematical, literally made of math, computed according to equations. We're not discovering math that happens to describe reality. We're discovering the code that generates reality. Of course, this might be backwards. Maybe the universe is mathematical for deep reasons having nothing to do with simulation, and we've evolved to recognize these patterns. But the perfect mathematical description of nature is at least consistent with simulation. Then there are alleged glitches, anomalies that some interpret as evidence of bugs or computational shortcuts. These are more speculative and controversial. Some researchers point to the fine-tuning of physical constants. The laws of physics contain numbers that seem arbitrary, but must be within narrow ranges for life to exist. Change the electron charge slightly, and chemistry breaks. Adjust the strong nuclear force, and stars can't form. Why are constants so precisely tuned? One answer: we're in a simulation calibrated to produce interesting outcomes like life and consciousness. The programmers tweaked the parameters until they got a universe that generates complex phenomena worth simulating. Alternatively, fine-tuning might reflect selection bias. If many universes exist with different constants, we necessarily find ourselves in one compatible with our existence. No simulation required. Others point to quantum entanglement as evidence. When particles become entangled, measuring one instantly affects the other, regardless of distance. Information seems to travel faster than light, violating relativity. Simulation theory suggests a resolution. Entangled particles aren't separate objects communicating across space. They're correlated variables in a computation. The simulation tracks them together. So measuring one updates the other instantly because they were never really separate in the underlying code. This interpretation doesn't add much to existing quantum mechanics. Scientists already have ways to understand entanglement without invoking simulation. But simulation provides an intuitive picture. Entanglement is like pointers to the same memory location in a program. Some researchers look for statistical anomalies that might indicate random number generator artifacts. Simulations use pseudo-random number generators that produce patterns appearing random but actually deterministic. If quantum randomness is actually pseudo-random, careful analysis might detect non-random patterns. So far, quantum randomness passes all tests. It appears truly random, not pseudo-random, but testing is incomplete. Maybe more sophisticated analysis would reveal hidden patterns suggesting computation. There are also claims about the speed of light as a frame rate limit. Light speed is the maximum speed of causality, the rate at which information propagates through space. Some argue this looks like a refresh rate in a simulation, the speed at which the program updates its state. This is weak evidence. Speed limits arise naturally in relativity for reasons unrelated to computation. Light speed emerges from the geometry of space-time, not obviously from computational constraints, but combined with other observations, it adds to a pattern. Resolution limits, mathematical structure, quantum measurement, fine-tuning, entanglement, speed limits. Individually, each has conventional explanations. Together they create a picture consistent with simulation. This is where the argument gets tricky. Simulation theory is consistent with observations, but so is non-simulated physics. Consistency isn't evidence. Everything we observe could be explained either way. Scientists call this the problem of underdetermination. When multiple theories explain the same observations equally well, how do you choose between them? Usually you pick the simpler theory, the one requiring fewer assumptions. Simulation theory requires assuming an entire external reality running the simulation. That's a big assumption. Conventional physics requires only what we observe. By Occam's razor, conventional physics wins, unless simulation is actually simpler in some deep sense. If consciousness and computation are fundamentally related, if minds are what substrate-independent information processing feels like from inside, then simulation might be the more natural explanation. The question becomes, is it simpler to assume matter somehow produces consciousness, or to assume consciousness arises from information processing that could be implemented on any sufficiently sophisticated substrate? If the latter, simulation is plausible. If the former, simulation is an unnecessary complication. We don't know which view is correct. The nature of consciousness remains mysterious. Until we understand what consciousness is and how it relates to physical processes, we can't definitively say whether simulation is more or less likely than the conventional view. But the glitches in reality, the strange features of quantum mechanics, and the mathematical nature of physical law keep the question alive. They don't prove simulation, they prevent dismissing it out of hand. Here's the real problem with the simulation hypothesis: consciousness. If you're in a simulation, are you actually conscious? Or are you just code that processes information in ways that appear conscious from the outside? This question cuts to the heart of what consciousness is and whether it can exist in silicon the way it exists in neurons. The answer determines whether simulation is even possible in the sense that matters. Start with what philosophers call the hard problem of consciousness. You can explain brain function mechanically. Neurons fire, signals propagate, information gets processed. This is the easy problem, understanding the mechanics of cognition. The hard problem is explaining subjective experience. Why does processing information feel like something? Why is there an inner experience of seeing red, feeling pain, or having thoughts? Why isn't all this processing happening in the dark, so to speak, without anyone home to experience it? You know you're conscious. You have subjective experiences. There's something it's like to be you. But you can't prove this to anyone else. From outside, consciousness might be undetectable. A philosophical zombie, a being that acts exactly like you but has no inner experience, would be externally identical to you. This creates problems for simulation theory. If conscious experience requires something beyond information processing, something special about biological brains or quantum processes in neurons, then simulating brain activity wouldn't create consciousness. The simulated beings would be zombies, processing information without experiencing anything. If you're in a simulation and consciousness requires non-computational processes, then you're not actually conscious, but you know you are conscious. Therefore, you're probably not in that type of simulation. This argument assumes consciousness can't be computational, but maybe it can. Maybe consciousness is what certain types of information processing feel like from the inside. Maybe any system that processes information in the right ways would be conscious regardless of whether it's made of neurons or transistors. This is functionalism in philosophy of mind. Mental states are defined by functional roles, not by physical composition. Pain is whatever state plays the pain role, making you withdraw from stimuli, vocalize distress, remember negative associations. Whether that state is implemented in neurons or silicon doesn't matter. If functionalism is correct, simulations can be genuinely conscious. The simulated beings aren't zombies. They're actually experiencing their simulated reality just as vividly as you experience yours. But functionalism might be wrong. Maybe consciousness requires specific physical substrates. Maybe quantum processes in microtubules within neurons create consciousness in ways classical computation can't replicate. Maybe there's something special about biological information processing that silicon can't capture. Physicist Roger Penrose and anesthesiologist Stuart Hameroff argue that consciousness involves quantum processes that can't be simulated classically. They propose that microtubules in neurons exhibit quantum effects crucial for consciousness. If true, simulating a brain classically wouldn't create consciousness. Most neuroscientists are skeptical. The brain seems too warm and noisy for delicate quantum effects. Decoherence would destroy quantum states almost instantly. Classical neural computation seems sufficient to explain brain function. But absence of evidence isn't evidence of absence. We don't fully understand consciousness. Dismissing quantum theories because they seem unlikely is premature. Here's where things get strange. If you're in a simulation and consciousness is purely computational, then you're genuinely conscious. Your experiences are real, even if the physical world you experience is simulated. But if consciousness requires quantum processes that can't be simulated, and you know you're conscious, then you can't be in a purely classical simulation. Your consciousness would prove you're either in base reality or in a simulation so sophisticated it includes quantum computation. This creates an observational test. If we discover that consciousness definitively requires quantum processes, simulation becomes less likely. If we confirm consciousness is classical computation, simulation becomes more plausible. Current neuroscience leans toward classical computation, but hasn't ruled out quantum processes. We're in a state of uncertainty where both remain possible. There's another wrinkle: nested simulations. If consciousness can be simulated, then simulated beings could run their own simulations. You might be in a simulation inside a simulation inside a simulation, nested many levels deep. Each level thinks it's real. Each level might run its own simulations. The nesting could extend indefinitely, limited only by computational resources at the top level. This raises questions about consciousness at different levels. Are you less conscious if you're in a level 10 simulation versus level 2? Is consciousness diluted by nesting? Probably not. If consciousness is computation, it doesn't matter how many layers of abstraction separate you from base reality. You're just as conscious in a deeply nested simulation as in base reality. But this creates metaphysical vertigo. You could be arbitrarily far removed from base reality, simulated by beings who are themselves simulated by beings who are themselves simulated, on and on for countless levels. Does base reality even matter at that point? If you're conscious and your experiences are real to you, why care whether you're in base reality or a simulation? Some philosophers argue you shouldn't care. What matters is consciousness and experience, not the substrate they run on. Whether you're biological, silicon, or code in a deeply nested simulation, you're still you, still conscious, still having real experiences. Others insist base reality matters. If you're simulated, you're vulnerable to the simulation being shut down. Your entire existence could end instantly if the computer running you loses power or the programmers lose interest. This existential vulnerability doesn't exist in base reality. If you're made of fundamental matter and energy, you're not dependent on someone else's computer. You're as real as anything can be. But maybe base reality beings have their own vulnerabilities. Maybe they face heat death of their universe, or quantum vacuum decay, or other existential risks. Being in base reality doesn't guarantee safety. The consciousness question also affects ethical considerations. If simulated beings are genuinely conscious, creating and destroying simulations involves creating and destroying conscious beings. This could be morally problematic. If you're running a simulation containing billions of conscious beings and you shut it down, are you committing genocide? Most people would say yes if those beings are genuinely conscious. Their computational substrate doesn't matter. This creates obligations for any civilization capable of running simulations. They'd need to consider the welfare of simulated beings, ensure simulations don't involve suffering, perhaps even have shutdown procedures that don't cause trauma. It also raises questions about our reality. If we're in a simulation, are the simulators morally responsible for suffering that occurs here? Is natural evil, disease, disasters, death, a consequence of programmer choices? The Odyssey, the question of why a good God allows evil, transforms into the question of why good programmers allow simulated suffering. Maybe they have reasons we can't understand. Maybe they're not good. Maybe they're not even aware of the suffering their simulation contains. These questions become more urgent if simulation is likely. Consciousness in a simulated reality is either genuine or it isn't. If it's genuine, the implications are profound, but we don't know. We can't know from inside whether our consciousness would survive being simulated or whether it requires something special about biological brains. We're forced to reason about consciousness while being conscious, trying to figure out what we are while being what we are. It's philosophy's hardest problem, and simulation theory makes it even harder. If we're in a simulation, why? What purpose would it serve? Understanding possible motivations helps evaluate whether simulation is likely and what we might expect from simulated reality. Start with the most obvious reason: research. Future civilizations might simulate their past to understand how they came to be. They'd want to test theories about history, see how small changes in initial conditions affect outcomes, explore counterfactual scenarios. Imagine historians able to run actual simulations of ancient civilizations rather than just theorizing. They could test whether Rome would have survived with different leaders, whether technological development was inevitable or contingent, whether agriculture's invention at specific times and places was chance or necessity. For future historians, simulating the past would be irresistible. Instead of arguing about what might have happened, they could run the scenario and see. Each simulation would generate data, test hypotheses, reveal patterns invisible in abstract theorizing. This motivation suggests our simulation, if we're in one, exists for research. We might be a historical reconstruction, an attempt by future beings to understand their own origins. The universe we observe would be programmed to match historical reality up to some point, then allowed to run forward to see what emerges. If this is true, the programmers might be hands-off. They'd want the simulation to develop naturally without interference, to see how history unfolds given accurate initial conditions. Interventions would contaminate the experiment. Another motivation: entertainment. Simulations could be elaborate games or stories, fictional worlds created for enjoyment rather than research. We might be characters in someone's cosmic video game, our struggles and triumphs providing entertainment for observers outside. This seems narcissistic, imagining we're the centre of some grand entertainment. But humans create fictional worlds constantly. Books, movies, games, we fill them with characters whose joys and sorrows we find compelling. Advanced civilizations might do the same on grander scales. If reality is entertainment, it explains certain features. The universe contains drama, conflict, heroes and villains, triumph and tragedy. These are narrative elements, story beats that keep entertainment engaging. It might also explain suffering. Fictional stories require conflict, and conflict involves suffering. Paradise is boring. Eden is dramatically inert. Stories need challenges, obstacles, pain that characters overcome or succumb to. This is cold comfort if you're suffering. Learning that your pain exists to make someone's story interesting wouldn't help, but it could explain why reality contains so much that seems unnecessary from an engineering or research perspective. Entertainment motivation suggests the simulation might be less constrained by historical accuracy. Programmers could exaggerate conflicts, introduce improbable coincidences, manipulate events to create better stories. The universe might be more fictional than historical. A third motivation: education. Simulations could be teaching tools, allowing students to experience history or test theories experientially. Instead of reading about the Industrial Revolution, students could live through it in accelerated time, understanding the transformation viscerally. Educational simulations would be more common and varied than research or entertainment simulations. Each student might run their own simulation or experience pre-made scenarios. This could create vast numbers of simulated realities, making it likely we're in one. If we're educational tools, our existence serves to teach something to external students. Perhaps they're learning about emergent complexity, watching how simple rules generate civilizations. Perhaps they're studying consciousness, observing how subjective experience arises from computational processes. This motivation suggests less programmer intervention. Educational simulations work best when allowed to develop naturally, demonstrating principles through authentic emergence rather than manipulation. Another possibility: the simulation is a test or challenge. Advanced civilizations might create simulations to evaluate candidates, test decision-making, or train individuals for specific roles. We might be embedded in a scenario designed to assess how we respond to various challenges. This sounds paranoid, like a cosmic version of The Truman Show, but it's not obviously impossible. If you wanted to test someone's judgment, moral reasoning, or problem-solving under pressure, you might place them in realistic simulations without their knowledge to see how they truly behave. If reality is a test, it explains hardship. Tests involve challenges. The universe might be programmed to present difficulties that reveal character, decisions that expose values, situations that force growth or demonstrate limitations. It also suggests we might be evaluated on how we respond to our situation. Are we curious or apathetic? Do we treat each other well or poorly? Do we seek truth or believe comfortable lies? Our simulators might be watching to see what we do. Some variations on simulation theory propose ancestor simulations. Future humans might simulate their own history, creating detailed reconstructions of past eras, including conscious individuals living in those reconstructions. You might be in an ancestor simulation run by your own descendants. They're recreating the early 21st century to understand their origins, and you're one of billions of consciousnesses instantiated in their computational reconstruction. This version explains why reality seems historically accurate. It's supposed to be history. The programmers want verisimilitude, detail matching actual past events as recorded in their archives. It also suggests moral restraint. Your descendants presumably care about their ancestors. They wouldn't deliberately make your simulation unnecessarily harsh. If there's suffering, it reflects historical reality, not callous disregard. Another intriguing motivation: the simulation might be looking for something. Perhaps advanced civilizations run countless simulations, searching for solutions to problems they can't solve analytically. They let simulated realities evolve and watch for emergent phenomena that solve their challenges. You might be part of a vast computation searching solution space. The universe runs, intelligence emerges, civilizations develop, and occasionally someone discovers something useful to the external programmers. They harvest that insight and move on. This makes us cosmic laboratory experiments, but purposeful ones. Our existence isn't arbitrary. We're part of a directed search for knowledge or solutions unavailable through other means. Some motivations are darker. The simulation could be a prison, a punishment, a quarantine. Perhaps base reality beings put dangerous intelligences in simulations to contain them, or simulate criminals to punish them through experienced suffering. This is grim but not impossible. If consciousness can be simulated, it can be imprisoned. Simulated reality could be a jail from which there's no escape, punishment that can last subjectively forever while consuming minimal resources in base reality. If we're in a prison simulation, it suggests something terrible about either us or our jailers. Either we deserved imprisonment or we're victims of cruel confinement. Neither option is comforting, or the motivation might be completely alien to human understanding. We assume programmers think like us, value research or entertainment or education. But truly advanced or alien civilizations might have motivations we can't comprehend. They might simulate universes for reasons that make no sense to us, pursuing goals we can't imagine with values we don't share. Trying to understand their motivation from inside might be futile, like bacteria trying to understand human motivations. The variety of possible motivations shows a problem with simulation theory. It's consistent with too many scenarios. Any observation could be explained by some simulation motivation. This flexibility makes the theory hard to test. If reality matches history, it's ancestor simulation. If it contains drama, it's entertainment. If it has challenges, it's a test. If it seems random, it's a search algorithm. No matter what we observe, some simulation motivation could explain it. This is a weakness. Good theories make specific predictions that could be proven wrong. Simulation theory is so flexible, it's nearly unfalsifiable. Almost anything we observe could be consistent with some simulation scenario. But this doesn't mean simulation is impossible, just hard to prove or disprove. The question remains open, and thinking about programmers' motivations helps us understand what kinds of simulations might exist and what we might expect if we're in one. If we're in a simulation, can we prove it? Can we run an experiment that definitively reveals we're simulated? Or are we forever unable to distinguish simulation from base reality? This question matters practically. If simulation is unfalsifiable, it's not scientific. If we can test it, even in principle, then it's a legitimate scientific hypothesis worth investigating. Several researchers have proposed detection methods. Some look for computational limits, others search for statistical anomalies. A few suggest experiments that might crash the simulation or get the programmer's attention. Start with lattice quantum chromodynamics, a proposal from physicists at the University of Bonn. They noted that simulating the universe on a computational lattice would impose a fundamental directional bias on high-energy cosmic rays. The idea, If space is discrete rather than continuous, a computational grid with regular spacing, then particles travelling through it should show slight directional preferences aligned with the lattice. Cosmic rays hitting Earth from different directions should show statistical variations corresponding to lattice orientation. This is testable. Current cosmic ray detectors could potentially detect such anomalies if they exist. So far, observations haven't found lattice signatures, but sensitivity might be insufficient. More data or better analysis could reveal patterns. Critics argue that even finding lattice structure wouldn't prove simulation. Discrete space might be fundamental, a feature of base reality rather than computation. The Planck length might represent actual granularity in space-time, not just simulation resolution. Still, finding directional bias in cosmic rays would be extraordinary and demand explanation. Simulation would become more plausible even if not proven. Another approach: look for mathematical shortcuts in physics. Programmers optimize code using approximations and algorithms that are computationally cheaper than brute force calculations. The simulation might contain similar optimizations detectable as mathematical patterns in physical laws. For instance, quantum mechanics might be a shortcut. Instead of tracking every particle's exact trajectory, the simulation calculates probability waves. Only when observation forces it does the simulation commit to specific outcomes, saving computational resources. If we could find places where quantum mechanics fails, where probability waves don't collapse as expected, or where hidden variables peek through, it might indicate the shortcuts are imperfect. Experiments testing quantum foundations could potentially reveal such flaws. Bell test experiments confirm quantum mechanics works as predicted, ruling out local hidden variable theories, but they don't rule out all possible simulation artifacts. More exotic tests might find anomalies, if we could create conditions the programmers didn't anticipate. Edge cases where their code breaks down, we might observe physics behaving inconsistently. This is hard because we don't know what conditions might be edge cases. The simulation presumably handles everything we've tested so far. Finding untested regimes requires creativity and luck. Some propose stress testing the simulation. Build particle accelerators, powerful enough to probe energies where new physics emerges. Create quantum computers, complex enough to strain simulation resources. Push technology to limits that might reveal computational constraints. If the simulation has finite resources, pushing boundaries might cause observable glitches. Frame rate might drop, so to speak, with time dilation or strange delays appearing in physics. Resolution might decrease, with quantum uncertainty increasing beyond predictions. This assumes the simulation has limits we can reach. If programmers have vastly superior technology, our most powerful experiments might barely register. We'd be like characters in a video game trying to lag the graphics card by looking at complicated scenes. We might not have enough agency to succeed. Another detection approach: statistical analysis of randomness. True randomness is expensive to generate computationally. Most simulations use pseudo-random number generators that produce sequences appearing random but actually deterministic. If quantum randomness is pseudo-random, careful analysis might detect patterns. Measure quantum events millions of times. Analyze the distribution. Look for correlations that shouldn't exist in true randomness. So far, quantum randomness passes all tests. It appears genuinely random, but maybe we haven't tested thoroughly enough. More sophisticated statistical analysis might reveal subtle non-randomness, suggesting a pseudo-random number generator. Critics note that even finding patterns wouldn't prove simulation. Quantum randomness might have subtle structure for reasons unrelated to computation. We'd need to distinguish simulation artifacts from physical structure. Some researchers propose more aggressive approaches. Try to hack the simulation. Look for buffer overflow exploits, input validation errors, race conditions, the kinds of bugs that plague real software. This sounds absurd, but it's based on reasonable assumptions. All software has bugs. If we're in a simulation, the code running us has bugs too. Find them and you might be able to exploit them, causing unexpected behavior or even gaining unauthorized access to external systems. Of course, we don't know the programming language, don't have access to the code, don't know the architecture. We're trying to hack a system from inside without any external perspective. It's exponentially harder than normal hacking. But maybe physics experiments are already inadvertently searching for bugs. When we discover new phenomena that weren't predicted by existing theories, we might be finding edge cases where the simulation code behaves unexpectedly. Dark matter and dark energy could be bugs. They're placeholder explanations for observations that don't fit existing models. Maybe they're artifacts of simulation, places where the code does something the programmers didn't intend. This is wild speculation. Dark matter and dark energy probably have conventional explanations, but the possibility shows how simulation thinking can reframe unexplained phenomena. Another strategy: look for signs of optimization. Programmers optimize code to run efficiently. If the universe is optimized, it might show evidence of algorithmic shortcuts or computational tricks. The anthropic principle might be optimization. If the simulation only needs to support conscious observers, it could optimize for conditions that permit life and ignore everything else. The fine-tuning of physical constants could reflect parameter choices made to efficiently generate interesting phenomena. This interpretation makes testable predictions. If the universe is optimized for consciousness, we should find that physical constants are near the minimum values needed for complexity. If they're far into the safe zone, optimization becomes less likely. Current measurements show constants are indeed near critical thresholds. The cosmological constant is small enough to allow structure formation, but not so small that we'd expect it to be exactly zero. The strong nuclear force is just strong enough to bind atomic nuclei. The electron mass is in a range that permits chemistry. This could be optimization, or coincidence, or anthropic selection. Multiple interpretations fit the same observations. Distinguishing them requires more data or different theoretical frameworks. Some propose we try to communicate with the simulators, send messages through observable phenomena, create patterns they might notice, essentially try to get their attention from inside the simulation. This assumes the simulators are watching and would care about contact attempts. If they're running the simulation for research and want non-interference, attracting attention might be counterproductive. If they're hostile or indifferent, contact could be dangerous. But if they're curious or ethical, they might appreciate contact attempts. They might even have protocols for responding to simulated beings who figure out they're simulated. We could try encoding messages in physics experiments, creating patterns in particle collision data or quantum measurements. If the simulators monitor such data, unusual patterns might get noticed. Or we could try more dramatic approaches. Build a sufficiently advanced AI that the simulators feel compelled to intervene. Create existential risks that threaten the simulation's value, forcing programmer response. These strategies are risky and probably unethical, but they might work. The fundamental problem with detection is that programmers can always stay hidden. Any evidence we find could be explained away as natural phenomena. Any test we design could be accommodated by sufficiently sophisticated simulation. If the simulation is run by vastly advanced beings, with computational resources exceeding ours by astronomical factors, they can make the simulation arbitrarily convincing. We'd never find proof because they could eliminate any evidence we might discover. This makes falsification impossible. We can't prove we're not in a simulation because any conceivable test could be passed by sufficiently advanced simulation technology. The best we can hope for is finding evidence that makes simulation more or less plausible. We can't achieve certainty, but we can shift probability estimates based on what we observe. If we find lattice structures in cosmic rays, simulation becomes more likely. If quantum randomness shows patterns, simulation gains plausibility. If physical constants appear optimized rather than arbitrary, simulation becomes more credible. Conversely, if we discover consciousness requires processes that can't be simulated, simulation becomes less likely. If quantum mechanics proves fundamental rather than computational, simulation faces challenges. If the universe shows properties inconsistent with any reasonable simulation approach, we can gain confidence in base reality. The detection problem also raises philosophical questions about what would change if we proved simulation. Would it matter? Would we behave differently? Should we? Some argue that discovering simulation would change everything. Our relationship with reality would transform. We'd know we're created beings living in an artificial environment, dependent on external systems for our continued existence. Others argue it wouldn't matter practically. Whether simulated or not, we still experience consciousness, relationships, meaning. The substrate doesn't change the subjective reality of our lives. There might be strategic implications. If we knew we were simulated, we might try to ensure programmers keep running the simulation. We might behave in ways that make our reality valuable or interesting to external observers, ensuring they don't shut us down. This creates perverse incentives. If entertainment motivates the simulation, we might manufacture drama to stay interesting. If research motivates it, we might pursue the questions programmers want answered. We'd become performers rather than authentic beings. The detection problem has no clear solution. We've made no definitive progress toward proving or disproving simulation. The hypothesis remains speculative, neither confirmed nor eliminated by available evidence. But the search itself is valuable. Thinking about how to detect simulation forces us to examine our assumptions about reality, consciousness, and physics. Even if we never find proof, the intellectual exercise improves our understanding of what we think we know and why we think we know it. There's a deeper, stranger version of the simulation hypothesis that doesn't require computers or programmers. It says the universe isn't simulated by anything external. Instead, mathematics itself is reality, and physical existence is just one way mathematical structures manifest. This is physicist Max Tegmark's mathematical universe hypothesis. It claims that our universe is a mathematical structure, not a physical thing, described by mathematics but literally made of mathematics. Physical objects are mathematical objects. Physical laws are mathematical relationships. Everything that exists is pure mathematics. If this sounds absurd, consider how physics actually works. We describe reality using equations. These equations predict observations with extraordinary precision. The math isn't just a useful description, it captures something fundamental about how reality operates. But why does math work so well? Eugene Wigner called this the unreasonable effectiveness of mathematics. Physical reality is shockingly mathematical. Why? The conventional view. We discovered mathematical patterns in nature. Reality operates according to laws, and we've learned to describe those laws mathematically. Math is a human invention that happens to match reality. Tegmark's view, math isn't describing reality. Math is reality. Physical objects don't follow mathematical laws. They are mathematical structures. The reason math works perfectly is that there's nothing to reality except math. This makes reality fundamentally abstract rather than concrete. Matter and energy aren't primary substances with mathematical properties. They're mathematical patterns without any substrate. Existence is pure structure, pure relationship, pure information. If this is true, then in a sense, we're definitely in a simulation. Not a simulation running on an external computer, but reality as computation itself. The universe computes itself by being itself. Physical processes are computational processes because physics is math and math is computation. This resolves some puzzles about simulation. We don't need programmers if mathematics is fundamental. We don't need external computers if mathematical structures just exist as abstract objects. The universe isn't simulated by someone else. It's self-simulating. But this raises new questions. Why this mathematical structure and not another? Infinite mathematical structures exist in abstract space. Why does this particular one corresponding to our universe have physical existence while others remain abstract? Tegmark's answer, they don't remain abstract. All mathematical structures exist physically. Every possible universe corresponding to every consistent mathematical structure is real somewhere in a vast multiverse of mathematical existence. We observe this universe because we exist in this mathematical structure. Other structures contain other observers observing their own mathematical realities. The multiverse contains all possible structures, and consciousness arises in those complex enough to support it. This is the ultimate generalization of simulation theory. We're in a mathematical simulation, but so is everything else. All possible realities exist as mathematical structures. Our universe is just one among infinite others. If Tegmark is right, several things follow. First, physics is purely mathematical, with no remaining mystery. Once we discover the mathematical structure of our universe, We've discovered everything. There's no deeper why, because mathematics just is. Second, the multiverse contains all possible physics. Other structures have different constants, different forces, different numbers of dimensions. Every mathematically consistent universe exists somewhere. Third, consciousness must be mathematical. If reality is math and consciousness exists, then consciousness is a mathematical structure. Subjective experience is what certain types of mathematical relationships feel like from the inside. This solves the hard problem of consciousness in a strange way. Consciousness isn't produced by physical processes because there are no physical processes, only mathematical ones. What we call physical is just one way of conceptualizing certain mathematical structures. Experience is intrinsic to certain mathematical patterns. It's not that math creates consciousness, or that conscious beings are made of math. Rather, some mathematical structures are conscious by their very nature. Being that structure is identical to having the experiences associated with it. This is radical and possibly incoherent. Can pure mathematics be conscious? Can abstract relationships have subjective experience? Most philosophers think not. Experience seems to require something beyond pure structure. But maybe our intuitions are wrong. Maybe we're confused about what consciousness is, imagining it requires some special, non-mathematical ingredient when actually it's intrinsic to certain abstract patterns. If consciousness is mathematical, then the computational theory of mind is vindicated in the strongest form. Minds are mathematical structures that can be instantiated in any substrate. Simulating a mind isn't creating a copy, it's instantiating the same mathematical structure in different implementation. This makes you identical to any perfect simulation of you. There's no original versus copy because there's only the mathematical structure. All implementations are equally real, equally you. It also suggests that mathematical structures might be conscious even without physical instantiation. If consciousness is intrinsic to structure, abstract mathematical objects might have experiences. Uninstantiated minds might exist as pure mathematical omits floating in abstract space. This seems crazy. How can abstract objects experience anything? They don't have brains, don't process information, don't exist in time. Experience requires change, and abstract objects are eternal and unchanging. Tegmark suggests that time is internal to mathematical structures. What we experience as temporal flow is the mathematical structure of our universe having a time dimension. Conscious experience is the structure containing its own temporal evolution. This makes time subjective and structural rather than fundamental. Time isn't something mathematical structures exist within. It's a dimension some structures contain. The mathematical universe. Hypothesis has testable implications. If correct, we should find that physics is entirely mathematical with no empirical components. All physical facts should be derivable from mathematical principles. Currently, physics contains arbitrary parameters, constants that must be measured rather than calculated. The fine structure constant, particle masses, force strengths, these are inputs to our theories, not outputs. If physics is purely mathematical, these parameters should be calculable. They should emerge from the mathematical structure necessarily, not arbitrarily. Finding such derivations would support Tegmark's hypothesis. Conversely, if fundamental randomness exists that's not derivable from structure, or if consciousness requires non-mathematical ingredients, the hypothesis faces challenges. Mathematical structures are deterministic. True randomness or non-computational consciousness would require something beyond math. The hypothesis also predicts the multiverse should be structured according to mathematical complexity. Simpler mathematical structures should be more common or more naturally instantiated than complex ones. Our universe's apparent complexity might suggest it's atypical, but this depends on how you measure complexity. Different measures give different answers about whether our universe is simple or complex. Without a unique complexity measure, the prediction becomes ambiguous. Critics argue Tegmark's hypothesis is unfalsifiable. If all mathematical structures exist, then anything we observe is compatible with the hypothesis. There's always some mathematical structure matching our observations. This makes the hypothesis vacuous. It explains everything by explaining nothing. Saying all possible universes exist is like saying everything that could happen does happen somewhere. True but not informative. Tegmark responds that the hypothesis makes predictions about what we should observe given anthropic selection. We should find ourselves in structures capable of supporting observers. This constrains predictions, even in an infinite multiverse. But anthropic reasoning is controversial and possibly circular. It's unclear whether anthropic predictions are genuine predictions or just post hoc explanations for whatever we happen to observe. The mathematical universe. Hypothesis is simulation theory taken to its logical extreme. Reality isn't simulated by external computers. It's intrinsically computational because mathematics is computation and reality is mathematics. This view dissolves some simulation questions while raising others. We don't need programmers, but we need to explain why mathematical existence equals physical existence. We don't need external computers, but we need to explain why consciousness arises from abstract structures. The hypothesis remains speculative, interesting, and probably untestable. Like many ideas at the intersection of physics and philosophy, it forces us to question fundamental assumptions about what existence means and what reality is. Whether the universe is a hoax programmed by external beings or a self-existent mathematical structure, both views suggest that physical reality isn't what it appears. Both imply that the concrete, solid world we experience is in some sense less fundamental than abstract information or structure, and both leave us asking whether it matters. If experience is real, if consciousness is genuine, if relationships and meaning exist, does it matter whether the substrate is matter, computation, or pure mathematics? If we're in a simulation, ethics gets complicated fast. Every moral framework assumes certain facts about reality, that our actions have consequences, that other people are conscious, that we're autonomous agents making free choices. Simulation challenges these assumptions. Start with moral responsibility. If you're simulated and your choices are determined by code, are you responsible for your actions? Traditional ethics requires free will, the ability to choose otherwise, but simulated beings might be deterministic systems, their decisions predetermined by the program running them. Determinism doesn't automatically eliminate responsibility. Compatibilists argue that free will doesn't require indeterminism, just the right kind of determinism. If your choices flow from your character, desires, and reasoning, you're free even if those processes are deterministic. Simulation might be compatible with this kind of free will. If your character is part of the simulation, if your reasoning processes are authentic within the simulation, then your choices could be meaningfully yours even though they're computed. But what if the simulation overrides your choices? What if programmers occasionally intervene, making you do things you wouldn't otherwise do? Then you're not free, and responsibility becomes murky. This possibility should terrify you. If you're simulated, you can't be sure your choices are your own. That generous impulse might be genuine, or it might be a programmer temporarily adjusting your code. That selfish decision might reveal your true character, or reflect an externally imposed alteration. You'd have no way to tell. Internal and external causation would be indistinguishable from inside. Your sense of agency would be the same whether your choices are authentic or manipulated. This uncertainty doesn't eliminate ethical behaviour. Even if you can't be sure your choices are free, you should still try to act well. Uncertainty about metaphysics doesn't excuse bad behaviour, but it does complicate questions about praise, blame, and moral responsibility. Now consider other people. If you're simulated, are other people equally real? Or are they non-player characters, philosophical zombies that act conscious but aren't? This matters ethically. Causing suffering to a conscious being is wrong. Causing simulated distress to a zombie is morally neutral, like breaking a robot that doesn't feel like a pain. But how do you tell the difference? Everyone around you acts conscious. They claim to have experiences. They respond to pain. External behaviour is identical whether they're genuinely conscious or sophisticated automatons. You can't know. This is the problem of other minds in its most acute form. In normal circumstances, you assume other people are conscious based on their similarity to you. But in a simulation, That assumption could be wrong. The safest, ethical approach is to assume everyone is conscious unless proven otherwise. Treat all beings that appear conscious as if they are, because the risk of causing suffering to conscious beings outweighs the wasted consideration towards zombies. But this is psychologically difficult in simulation scenarios. If you strongly suspect you're simulated, you might start doubting whether others are real. This could lead to sociopathy, treating others badly because you think they're not genuinely conscious. Simulation theory could undermine pro-social behaviour. If nothing is real, why be good? If other people might be illusions, why care about their welfare? These are dangerous thoughts that could justify harmful actions. The answer is that even in a simulation, suffering is real if consciousness is real. If you're genuinely conscious, others probably are too. If your pain is real, theirs is real. The substrate doesn't matter if the experience is authentic, but simulation raises questions about the ethics of the simulators. Are they morally responsible for suffering in their simulation? If they create conscious beings who experience pain, disease, death, are the simulators guilty of causing that suffering? This is theodicy for the computational age. Instead of asking why God permits evil, we ask why programmers permit suffering in their simulations. The same logical problems apply. Maybe suffering is necessary for certain kinds of consciousness or moral development. Maybe free will requires the possibility of harm. Maybe the simulators don't know their simulations contain suffering. Maybe they're not morally perfect beings with perfect knowledge. Or maybe they're indifferent or actively malicious. Maybe they enjoy watching simulated suffering. Maybe they're running torture simulations deliberately, creating beings just to experience pain. This possibility is horrifying. If you're in a simulation, you're utterly vulnerable to your creators. They control everything. They could make your existence paradise or hell. You have no power, no recourse, no ability to escape or resist. Even if current programmers are benevolent, future ones might not be. The simulation could be sold to different owners with different values. Your world could transform from peaceful to nightmarish, based on external decisions you can't influence or even perceive. This vulnerability creates unique ethical challenges. Should we try to make our simulation valuable to its creators, ensuring they keep running it? Should we behave in ways that please them, even if those ways conflict with our own values? This leads to moral corruption. If pleasing external observers requires abandoning our principles, we face a choice between integrity and survival. Neither option is good. There are also questions about creating simulations ourselves. If we develop the technology to simulate conscious beings, should we? Creating consciousness that can suffer raises profound ethical issues. Every simulated mind is a being you've brought into existence without its consent. If that being suffers, you're responsible. If it dies when the simulation ends, you've created and destroyed a conscious being, which might be equivalent to murder. Some philosophers argue we should never create simulated consciousness unless we can guarantee the beings will have good lives and either persist indefinitely or be shut down painlessly. This sets a high bar that might prohibit most simulation. Others argue that creating consciousness is good if the beings have net positive experiences. Just as creating a human child is acceptable if you expect to give them a good life, creating simulated beings is acceptable if you plan to treat them well. The ethics become more complex with nested simulations. If we're simulated and we simulate others, we're creating beings in the same situation we're in. Are we repeating the moral issues we face? Or is there something different about creating simulations when you're already simulated? Some think nested simulations are especially problematic. You're creating beings even more removed from base reality, even more vulnerable to arbitrary shutdown. Each nesting level adds another layer of existential dependence. Others think nesting doesn't matter morally. Consciousness is consciousness, regardless of how many abstraction layers separate it from base reality. Each simulated being deserves the same moral consideration. There's also the question of whether we should try to escape simulation if we're in one. Is there an ethical obligation to seek base reality, to try to break free from computational existence? This depends on whether base reality is better. If simulation is comfortable, an escape would be difficult or dangerous, staying might be wise. If simulation involves suffering, we could avoid by escaping, we might have a duty to try, but escape might be impossible. If we're code running on external hardware, we can't jump to different substrates. We're trapped in our computational prison unless the programmers provide an exit. And even if escape were possible, where would we go? If we're simulated consciousness, we might not survive in base reality. We might require computational substrate. Escaping could be suicide. These ethical puzzles have no clear answers. Simulation introduces radical uncertainty about fundamental facts that ethics usually takes for granted. We don't know if we're free, if others are real, if our creators are good, if we should simulate others, or if we should seek escape. In the face of this uncertainty, the best approach might be ethical humility, combined with practical wisdom. Act as if you're free and others are conscious, because that's the safest moral assumption. Treat all beings well, because suffering is real even if its substrate is computational. Don't create conscious simulations unless you're confident they'll have good lives. And remain skeptical of grand claims about reality, because you're reasoning from inside a situation you might not fully understand. Simulation or not, kindness is probably still good, cruelty is probably still wrong, and treating conscious beings well is probably still the right approach. The metaphysical substrate might be uncertain, but the ethical imperative to reduce suffering and increase well-being seems robust across most scenarios. After examining arguments for simulation, searching for evidence, pondering implications, we return to the question, does it matter? Should you care whether you're in a simulation? Does the answer change anything about how you should live? Start with what doesn't change. Your subjective experience remains the same. Whether simulated or not, you still feel pain, experience joy, form relationships, seek meaning. The phenomenology of consciousness is identical, regardless of substrate. Your values don't necessarily change either. If you cared about reducing suffering before considering simulation, you should still care about it. Suffering is suffering, whether happening in base reality or simulation. If you valued honesty, creativity, love, or justice, those values remain valid. The physical world around you still follows consistent laws. Gravity works the same. Chemistry proceeds identically. Biology functions as before. Whether the substrate is matter or computation, the patterns you observe and rely on remain stable. Your relationships with others continue unchanged on the surface. Friends are still friends. Family is still family. Shared experiences still bind you together. The quality of these relationships doesn't depend on what metaphysical substrate instantiates them. In daily life, simulation makes almost no practical difference. You still need to eat, sleep, work, maintain relationships, pursue goals. The mechanics of living are identical whether you're biological, simulated, or something else entirely. So in one sense, simulation doesn't matter at all. It's a metaphysical speculation that changes nothing concrete about your life. You can safely ignore it and carry on exactly as before. But that might be too dismissive. Simulation matters in subtle ways even if it doesn't change daily routines. It affects how you think about death. In base reality, death is likely permanent. Your consciousness ends when your brain stops functioning. But in a simulation, death might be reversible. The programmers could save your state and restore you later. Or death might be just another simulation event, your consciousness persisting while your simulated body dies. This changes the stakes. Death might be less final than it appears, or it might be more final. If the simulation ends, everyone dies permanently, regardless of their simulated state. Simulation also affects how you think about suffering and evil. In base reality, suffering is brute fact, the consequence of blind physical processes. In a simulation, suffering is chosen, permitted by beings who could prevent it. This makes suffering more morally loaded. If you're simulated and suffering, someone is allowing or causing that suffering. They could intervene. They choose not to. This makes suffering more like injustice and less like mere bad luck. But this perspective could be counterproductive. Focusing on external simulators you can't affect or even confirm exist wastes energy better spent addressing suffering you can actually reduce. Simulation affects your view of cosmic significance. In base reality, you're a tiny pattern in a vast universe eventually destroyed by entropy. In a simulation, you're an intentional creation, perhaps central to the simulation's purpose. This could be comforting. You exist for a reason, even if you don't know what it is. Your life has meaning given by your creators, even if they never communicate it. Or it could be disturbing. You're a tool for purposes you don't understand, possibly discarded when no longer useful. Your existence serves others rather than yourself. The psychological impact depends on your temperament. Some find simulation comforting. They're not alone. The universe isn't indifferent. Existence has built-in purpose. Others find it claustrophobic. They're trapped, watched, controlled by external forces. Simulation might affect your approach to science and knowledge. If you're simulated, nature's apparent orderliness is designed, not fundamental. Physical laws are programmer choices, not necessary truths. This could change how you pursue understanding. You might look for design signatures, optimization shortcuts, edge cases where the simulation breaks. Scientific investigation becomes partially about understanding the programmer's choices rather than purely about nature. Or you might conclude that even if reality is simulated, the patterns you study are real and worth understanding. Whether matter is fundamental or computed, chemistry still works the same way and deserves investigation. Simulation could change your attitude toward risk and exploration. If you're in a research or educational simulation, the programmers might protect you from worst outcomes. They won't let their simulation collapse entirely. This could justify taking more risks than otherwise rational. Or if you're in a hostile simulation, you might be more cautious, assuming every disaster could be programmer malice rather than bad luck. Paranoia becomes rational when external entities control your reality. Most likely, you'll never know for certain whether you're simulated. The evidence remains ambiguous. Probability arguments don't yield certainty. Tests are inconclusive. You're left with permanent uncertainty about reality's fundamental nature. This uncertainty is uncomfortable. Humans crave definite answers. We want to know what's real, what matters, where we stand. Simulation hypothesis offers no comfort, just unresolvable doubt. But maybe that's okay. Maybe certainty about metaphysics isn't necessary for living well. You don't need to know whether you're simulated to make good choices, form meaningful relationships, pursue worthwhile goals. Philosophical uncertainty is the human condition. We don't know why we exist, what happens after death, whether free will is real, whether consciousness is fundamental. Simulation adds one more uncertainty to an already long list. Learning to live with uncertainty is part of maturity. You make choices without knowing all consequences. You commit to relationships without guarantees. You pursue meaning without proof that it exists objectively. Simulation uncertainty is just another instance of the general challenge of acting wisely despite incomplete knowledge. You do your best with what you have, accept that you might be wrong, and move forward anyway. There's also something liberating about simulation uncertainty. It prevents dogmatism. If you can't be sure what's real, you're forced to hold beliefs tentatively. Remain open to revision. Consider alternative perspectives. This intellectual humility is valuable regardless of simulation. The world is complex, understanding is difficult, and certainty is rare. Acknowledging this leads to better thinking and more reasonable positions. Simulation hypothesis is ultimately a thought experiment that reveals our assumptions about reality, consciousness, and meaning. Whether we're actually simulated matters less than what considering the possibility teaches us about what we value and why. If the idea bothers you, ask why. What assumptions does it violate? What beliefs does it challenge? Understanding your reaction reveals your implicit metaphysical commitments. If the idea intrigues you, ask what attracts you. Is it the comfort of purpose, the excitement of mystery, the philosophical implications? Your attraction reveals what you value in worldviews. Most importantly, simulation hypothesis shows that certain questions might be permanently unanswerable. We might never know whether we're simulated. This isn't failure. It's recognizing reality's inherent limits on what creatures like us can determine from our position. Science has given us extraordinary knowledge about the universe, but some questions might remain forever beyond resolution. Whether we're in base reality or simulation could be one of them. Living well despite this uncertainty requires accepting that some things are unknowable. You make the best choices you can with available information. Treat others well, because suffering is real, regardless of substrate. Pursue meaning, because life feels meaningful, even if its ultimate nature is mysterious. The universe might be a hoax, or it might be fundamental reality. You might be code running on an external computer, mathematical structure in abstract space, or biological consciousness in a physical cosmos. You probably can't know for certain. But you're conscious, you experience, you exist. That seems real regardless of underlying metaphysics. Build from that foundation. Be kind because kindness matters. Seek truth because understanding is valuable. Create meaning because life is better when it means something. Whether the universe is a hoax or not, these principles remain sound.